Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. If you really want to see something trashy, look at this. I have here a sneaker that's tattered and worn. It's all full of holes and the laces are torn. A gift from my mother the day I was born. I love it because it's trash. Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. Here's some more rotten stuff. I have here some newspaper, 13 months old. I've wrapped this inside it, it's smelly and old. But I wouldn't trade it for a big pot of gold. I love it because it's trash. Yes, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. Now look at this rest of this junk. I've a clock that won't work and an old telephone, a broken umbrella, a rusty trombone, and I am delighted to call them my own. I love them because they're trash. Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash.
This is the song, la 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 la, Elmo's song. La 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 la, la 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 la, Elmo's song.
I like it.
La la la, la 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 la.
To think he wrote this alone.
La la la, la 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 la.
Catchy.
He loves to sing, la 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 la, Elmo's song.
Oh, sing it.
La 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 la, la 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 la, Elmo's song. He wrote the music, he wrote the words. That's Elmo's song.
Wow, that's great.
Yeah, I wish I had a song.
Yeah, but Big Bird can hear Elmo's.
How?
Well, just sing Big Bird instead of Elmo.
Great idea.
Here I go. This is the song, la 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 la, Big Bird song.
It works.
La 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 la, la 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 la, Big Bird song. La la la, la 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 la. La 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 la, Big Bird song. La 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 la, la 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 la, Big Bird song. I love the music, I love the words. That's Big Bird song. Your turn, Snuffle Pal.
All right, stand back. This is the song, la 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 la, Snuffy song.
Sing it, Mr. S.
La 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 la, la 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 la, Snuffy song. La la la, la 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 la. La la la, la 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 la. I love to sing la 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 la, Snuffy song. La 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 la, la 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 la, Snuffy song.
He wrote the music, we wrote the words.
That's Snuffy's.
That's Big Bird. That's Elmo's song. Oh yeah!
Hi, Bert.
Oh, hi, Ernie. Hey, I've been sitting here trying to think of what we could do with this here letter L.
Oh, well, let's see. You know, one thing you could sing sort of a la-la-la song with the letter L.
What do you mean?
Well, there are all kinds of pretty words that begin with L. You know, you could sing a few la-la-las and some pretty little words and you'd have a nice little song, you know,
La
Bert?
la la, like that?
Sure, go ahead. Try it.
Okay, let's see. La 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 la, lemon. La 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 la, light bulb.
Uh-huh.
La 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 la, lamppost. This is fun. La 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 la, lump in my oatmeal.
Well, that's not quite what I was thinking about, Bert.
No?
I mean, there are a lot of pretty L words, and I was sort of thinking of the ones that are more lilting and lovely. You know, like la 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 la, laughter.
Oh, yeah, I see.
La 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 la, lullaby.
Like that, huh?
La 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 la, lollipop. La 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 la, lights in the sky.
Oh, Ernie, I got a great owl word. This is a beauty. Oh, listen to this. La la la, linoleum.
No, Bert, listen to me. 'Cause L is such a lovely letter. For words like licorice and lace, the letter L lights up your face, so why not la 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 with me?
Down at Fraggle Rock.
Sunny day, sweeping out clouds away. On my way to where the air is sweet. Can you tell me how to get to Sesame Street? Come and play, everything's A-okay. Friendly neighbors there, that's where we meet. Can you tell me how to get to Sesame Street? It's a magic carpet ride. Every door will open wide to happy people like you. Happy people like, what a beautiful sunny day. Sweeping up clouds away. On my way to where the air is sweet. Can you tell me how to get to Sesame Street? 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 How to get to Sesame Street?
Morning, everyone. Okay, so apologies, we're 20 seconds ahead of schedule. I couldn't get the music quite to fit quite right. So welcome to the second session of our natural language processing module. So last week we talked about some of the kind of core concepts that underpin a lot of natural language processing approaches, particularly the concept of vectorization, which, as you'll recall, is where we are effectively turning text data into numbers. And also, we looked at the bag of words approach for that, but which is a very simple approach that we won't be using today. We'll be using a different vectorization approach later. But the principle's the same, that you're in some way turning text into numbers. But we also looked at some other aspects. We looked at concepts such as tokenization, concepts of the importance of case within text data. And we also looked at how we can produce some really pretty word clouds using the Python word cloud package as well. So today, in the two sessions we've got today, really are the meat of the natural language processing module. So this morning we're going to look at something known as named entity recognition. We're going to explain what that is, and also look at a fantastic package called Spacey, which does some amazing things, and we're going to talk a bit about how that works, because the way in which Spacey works is the way in which a lot of big language models have learned to work as well. And then this afternoon we're going to be looking at text classification, and specifically looking at sentiment analysis, although the principle will be the same regardless of how you want to classify your text. So looking at ways in which we can use AI to classify text into different classifications. So this morning we're going to start with named entity recognition. So let's start by talking about what we mean by that. So named entity recognition, often abbreviated to NER, it's a subfield of natural language processing. Basically, we're trying to use various different approaches, and we'll talk about the approaches we're going to be using via Spacey later, which tries to identify, extract, and classify automatically what we call these named entities. Now, named entities are things that are real-world objects that can be denoted with a proper name, and that's things like the names of people or places or things that are spelled with a capital letter, although not always. So those kinds of things might have a real physical existence. So Dan Chalk, I'm an example of a named entity. The University of Exeter, both of these things have physical existence and are named entities. But you can also have named entities that are more abstract, so things like discrete event simulation, which is the name of something, so that would classify as a named entity. HSMA is indeed an example of a named entity too. And we can have lots of different categories for named entities as well. And Spacey is basically one of the Python package that we're going to be using today. It's a widely used package in natural language processing for very good reason. It's a very, very powerful package, as hopefully you'll see today. And Spacey has its own set of categories for named entities. So sorry, I've just noticed Prince has just left the room. I'm going to take this opportunity to close the door. 2 seconds. Sorry. Okay, sorry. I just thought I'd take that advantage before we started meowing. Yeah, so Spacey's got its own basically categories of named entity. So this will vary depending on the package you're using. But if you're using Spacey, which we are, this is what we're going to be using. And we can have the category, for example, of person. That categorizes any named entities that are people, and that includes fictional people as well. NORP, which is nationalities or religious or political groups. FAC, which is facilities, which is things like buildings, airports, bridges. We can have organizations, geopolitical entities, things like countries, cities, counties. Locations, which are basically locations that are not GPEs, geopolitical entities, so things like lakes, mountain ranges, that kind of things, more Dartmoor, Exmoor, those kinds of things. Products, things like objects, vehicles, foods, events, so like named storms, battles, wars, that kind of thing, and so on and so on. And you can see there are huge amounts of different categories of potential named entities. Some of them might be a bit of surprise to you if you're new to named entity recognition, particularly these ones down the bottom. So dates are considered named entities. Times are considered named entities. So that's any time that is smaller than a day. Percentages, which include the percentage character, is considered a named entity. Monetary values, which include the unit of monetary values. Quantities, ordinals, so things like first, second, third, etc., and cardinals. So that's where basically numerals that don't fall under one of the other types here. So those things might surprise you. The good news is, so very often when you're doing named entity recognitions, these things might be useful, they may not be. But this is part of the reason why we not only identify them, but also try to classify them as well automatically. And that allows us to then ignore anything that we are not interested in. And it may well be that, depending on what you're doing, these things aren't of interest for your particular analysis. So why might named entity recognition be useful for health? That's obviously why we're doing this course, to teach you things that hopefully are useful when you're doing a bit of analysis or modelling within health, social care and policing. Well, let's think of some potential examples. We could, for example, automatically identify the conditions, the clinicians involved, patient names, etc., those kinds of things in some patient notes, and we could do that automatically. We could automatically identify various procedures that are undertaken in ambulance crew notes. We could potentially automatically identify the things that people are talking about when they fill in like a patient survey. And we can combine that with sentiment analysis, which is what we'll be doing this afternoon. So sentiment analysis will basically allow you to say, I think they're talking positively or negatively, and you can combine that with some named entity recognition and say, but what are they talking positively about? What are they talking negatively about? So you can automatically pick out the people, the places, the organisations, the locations they're mentioning. And do that automated and at scale. And we can also automatically identify things like key named entities in the analysis of social media posts, things that people are posting to the organisation or about the organisation. And indeed, we've had an HSMA project that's done that before, looking at police forces across the country and how people are tweeting about and to them. And there may well indeed be other application areas that you can think of as well for your own particular organisations. So to understand a little bit about named entity recognition and how it works, we're going to dive a little bit first into the concept of parsing. So parsing is a really important concept in natural language processing. A lot of natural language processing tasks that you'll do will involve some kind of parsing. And basically parsing just simply refers to the process by which we are analysing the structure of our text to try to work out the various roles that words are playing within a piece of text and how those words are relating to one another. And there's basically kind of two main kinds of parsing when we talk about parsing in natural language processing. There's syntactic parsing, which is looking at the syntax, and as coders, you're probably used to the concept of syntax now, but syntax basically just means the way in which words and phrases are arranged. So when you get a syntax error in Python, that's basically what it's saying, that things aren't arranged correctly. And that can include, in natural language processing, things like parts of speech, which we'll talk about in a moment, and also the relationships between words. But there's also something known as semantic parsing, which is where you're trying to understand the semantics, and by semantics we just mean the meaning of our text. And we're doing that by looking at the way in which words interact and how they play different roles to give meaning, to give context to our text. So we said that one of the things that syntactic parsing does is to identify these parts of speech, and parts of speech are actually really important whenever we're looking at natural language processing or any text data analysis, really. So what do we mean by parts of speech? Well, I would argue probably most of you, if not all of you, have learned about parts of speech before, but you may not have heard them referred to as parts of speech. But parts of speech, which are commonly referred to as POS or POS, basically refers to the categories that we assign to words in our language that describe their syntactic functions. And you're probably thinking, I've not learned about that, Dan. Well, this may look familiar. There are 9 parts of speech in the English language. You probably learned about them at school, and then you probably forgot about most of them, as most of us did. These are the 9 parts of speech of the English language. So we've got nouns, which are the names of people, places, ideas, things, that kind of thing. Pronouns, which are used in place of a noun, so me, he, she, and it, etc. We use that in place of a noun in our text. Verbs, which are actions or express being, a state of being. Adjectives, which are describing words for things, so they modify nouns or pronouns, they describe it in some way. Adverbs, which are the same, but they describe and modify verbs. These are probably a bit more familiar to you. Some of these you probably encounter a bit less frequently. So determiners are basically things that limit or determine a noun. So 2 dogs, the rabbit. 2 is playing the role of a determiner here. The is playing the role of a determiner here. Prepositions, which govern a noun or pronoun to express a relation with another word or element in the clause, which sounds very complicated. We basically mean things like by and to and at, so it kind of links it semantically in that way. And then we've got similarly, but slightly different, conjunctions, which are things that join words, phrases, or clauses. So things like words like and but and when, etc. And then probably my favourite, interjections, which are words that are used to express emotion. So the word hey could be used as an interjection, depending on the context. So these are the and obviously it varies on the language. In the English language, there are 9 parts of speech, and these are they. And the labelling of words in our text according to what their POS category is, so which one of these they belong to, is known as POS tagging. So it's parts of speech tagging, and it's a really important part of syntactic parsing when we're analysing text data. So just as an example, here we've got a piece of text. You'll be delighted to know in previous cohorts, this was actually an exercise that I sent you a way to manually POS tag this. And there was a lot of grammar-based exercises. You do not have those this year. You'll be delighted to know. So here we've got the grey horse in the field slowly eating some grass when she looked up and saw a bird fly onto the fence. The bird was then joined by 400 more birds. Wow, clearly the author had been watching too much Alfred Hitchcock. To POS tag that, we would look at each word and the role it's playing in this particular text. So the, pretty obviously a determiner there. Grey being an adjective because it's describing the noun of horse. In being a preposition because it's relating to where they are. The being a determiner. Field being a noun. Was being the past tense of to be, which is the verb. Slowly, which is an adverb because it's describing the verb of eating, etc., etc., etc. There is some weird stuff in there as well. It gets pretty complicated. So this one used to throw people off when we did it as an exercise. Too much Alfred Hitchcock. Here, to plays the role of an adverb, and much plays the role of an adjective. And basically here, the reason for that is that much, this word here, is describing the noun Alfred Hitchcock, and so therefore it is an adjective because it's describing a noun, and to plays the role of an adverb because it is modifying an adjective. I just love the complexities of grammar. So you'll be delighted to know you don't have to manually POS tag this today. So POS tagging is basically identifying those parts of speech within which each word in a sentence should be tagged. However, just to further sort of complicate things a little bit, you might think, oh, well, there's only 9 POS tags, right, Dan? Because if we've got an English piece of text, there'll be 9 POS tags. Now, I'm afraid there aren't, because although there are only 9 parts of speech in the English language, there are a POS tag will also identify other aspects as well as the part of speech itself. So things like whether the word is pluralized, the tense of the word, the voice being used, and lots more. And it gets quite complicated. And also, just to add a bit of complexity, as you may have already considered, the same word can have different POS tags depending on the context. It's not as though a particular word will always play the role of the same kind of part of speech. They will play different roles, potentially, depending on the text in which it lives. So, as an example, the word pen, well, that could be a noun, i.e. referring to a writing instrument, a pen that we write with, or it could be a female swan, or an animal enclosure. But it could also be a verb. In other words, to pen, to write something, or to pen, to put an animal in an enclosure. So we don't know. If we just have the word pen, we can't POS tag that. We need to understand and derive clues from the context of the text in which it lives. So if we then had the context of the full text, it said Dan asked Sammy if he could borrow her pen, we can then be more confident that it's playing the role of a noun here rather than a verb, because of the way in which this sentence is structured. Unclear why I want to borrow Sammy's female swan. So we've got that the same word can be POS tagged differently depending on the context of our text, and so the concept of POS tagging itself is not as simple as just seeing a word and saying, oh, that word, that's a noun, that is, because we know that a lot of words can play the role of different parts of speech depending on the text. We've just seen just one of many examples there. So we can't just do that simply. So instead, effectively, the kind of approaches we'll see are machines essentially making predictions about the particular part of speech tag for a particular word that lives in a particular piece of text. And it does so by looking at the words before and after. And modern natural language processing approaches use this kind of more predictive way of doing things. We'll come back to how they used to do things in a little bit. So the Spacey package that we're going to be using today basically does this by using a very complex type of model known as a transformer. And we're going to talk about transformers this morning, mostly so that you can understand them broadly, how they work. You do not need to understand all the details of them. They are very, very complicated, but they have totally transformed the world of natural language processing. And it is that's no exaggeration. These are incredibly powerful modelling approaches. So why are we doing all this? Well, POS tags in turn, once we've got things POS tagged, can be used to try and understand something about the semantics and the context of our text, and that can help us draw out information we need as well. So a lot of these approaches POS tag in order to understand and go on to do things like, for example, extract named entities, which is why we're here this morning. Okay, let's now talk a little bit about noun phrases, because they sound fun, don't they? Let's talk about noun phrases. What do we mean by a noun phrase? Well, a noun phrase is a phrase that is either headed by a noun or an indefinite pronoun. I'll talk more about what that is in a moment. Or they are headed by a word that will perform the same grammatical function as a noun and is essentially being used as a proxy. which is probably clear as mud. So let's try putting that another way. A noun phrase basically includes a head noun, so for example, cat, and the modifiers which identify it. So my cat is a noun phrase and cat is the head noun. John's cat is a noun phrase and cat is the head noun. The cat with white stripes. It's which cat is it? It's the cat with white stripes. Which cat is it? It's John's cat, etc. The cat who ate all the tuna. I think that's Prince. There may be other nouns in the noun phrase. Indeed, here is an example of where we've got two nouns in this two-word noun phrase. John is also a noun. But the one around which the phrase is semantically centered is the head noun. So here it's centered around the cat. And we're using the noun of John to identify the cat. It's all about the cat. It's always all about the cat, if you ask a cat. So let's look at some examples of here in some text. And I've underlined the noun phrase and I put the head noun of each noun phrase in bold. So the staff are very helpful, but the food was terrible contains two noun phrases: the staff being the head noun, and the food, with food being the head noun. A green-eyed Tom enviously watched Dan's amazing lecture. Again, two noun phrases. We've got a green-eyed Tom being the head noun. Which Tom is it? Well, it's the green-eyed one. And Dan's amazing lecture being the head noun. And which lecture was it? Well, it's Dan's amazing one. Probably doesn't narrow it down, but there we are. And then the notion of an enhanced greenhouse effect. This one particularly interesting. So the head noun, that whole thing is a noun phrase. Because which notion is it? Well, it's the notion of an enhanced greenhouse effect. So that's the head noun. But there are other contenders in here that could be head noun. Greenhouse and effect as well as notion. But greenhouse here is playing the role of an adjective, not a noun. And the word effect is playing the role of a noun in this noun phrase. But it is not the thing that we are semantically centered around. And a good way to try and get your head around that is to think, if the next sentence said it, what would we as a reader think it was referring to? And here we would think it's referring to correctly referring to the notion. So if we say the notion of enhanced greenhouse effect, it is something that is very important or whatever, we would think, oh well, that's relating to the notion. Okay. And so that's it's semantically centered around this head noun, and when we say it, we're referring back to that head noun in the noun phrase. Well, this is fascinating, Dan, but why are you talking to us about noun phrases, as fascinating as they are? Well, it's because named entities are effectively definite noun phrases that refer to specific types of individuals, such as organizations, persons, dates, so on. So they noun phrases are related to our problem here because they are definite noun phrases. Well, what, Dan, is a definite noun phrase? Well, a definite noun phrase is one where the head noun, remember that's the one we are semantically centered around, clearly refers to something specific. So something that is previously been mentioned or is can otherwise assumed to be previously known, something unique which makes it identifiable, or something that which is being identified by the speaker. And the head noun is prefaced by the definite article. The definite article is just a fancy word for the, unless the specificity that we are looking for is contained in the noun itself, such as an ordinal number. So we don't need the word the if we've got the word first, because it is already specific enough that the word first conveys the specificity, it is the first. Now, the definite article, just to add a little complexity here, may of course be followed by various adjectives. So, and we'll come back to that in a moment. So we could have I saw the fluffy cat on the comfy sofa. This is all very jolly, isn't it? This sounds great. The opposite of a definite noun phrase is, perhaps unsurprisingly, an indefinite noun phrase in which the head noun refers to a singular noun, but one in which the reader or the listener does not know exactly which one to which we are referring. So I sat next to a very fluffy cat would be an example of an indefinite noun phrase, because the a very fluffy cat would be the noun phrase, and it would be an indefinite noun phrase because we do not know which cat we are talking about. Therefore, it is an indefinite noun phrase. Wow, this is fun. This is grammar. It's a joy, isn't it? Absolutely a joy. Here's a kitten to calm us down, because apparently this is supposed to be fun. Right, so let's just review where we are so far. We know that named entities, remember those things, that's the thing, that's what we're looking for. This is the whole purpose of this morning. We're going hunting for named entities. We know that they are found in definite noun phrases, right? So we've got this piece of knowledge. We know that. That's a thing. And we also know that definite noun phrases will often have head nouns that are prefaced by the word the definite article, unless they are things like ordinal numbers, which inherently convey the specificity, so words like first, second, etc. So, in theory, is it not therefore relatively easy to identify at least the ones that are prefaced by the word the, just by looking for the word the followed by a noun? Surely we can just do that. No, we can't. We can't do that, and there are a number of reasons why we can't just apply that rule. First of all, we don't just refer to nouns by themselves, and we often use adjectives or other words that will complicate the sentence, so or modify the noun in some way. So as we've just seen, we might say the cat, but we could indeed also say the fluffy cat, and we'd need to pick up both examples consistently. We also, and this is a slightly more complicated problem, we also need to identify what the head noun is in a noun phrase, and there may be more than one contender. So the vicar, Brian, my cat, Bob, both examples of noun phrases where there are two nouns and we have to know which one is the head noun, or rather our algorithm needs to know and be able to identify which is the head noun. Now the old-fashioned way of doing this was, and we still use a little bit, but I mean the NLP world has basically moved on largely from this, except for some particular applications, was to use things known as regular expressions, or regex, which are basically sequences of characters that define search patterns, and then basically once you've POS tagged a document by identifying the parts of speech role that each word is playing within your text, you can then apply regular expressions to try to look for different syntactic patterns. So things like, you could say, okay, I'm looking for things where I've got a determiner followed by a noun, but also there might be an adjective in there as well. So you can look for those kinds of patterns to look for things like the cat or the fluffy cat. Now, and that allows us to do things like looking for definite noun phrases. We don't use regular expressions on HSMA, and indeed most of the NLP world has indeed moved on, and I would argue for 4 key reasons. The first reason, which I would see probably the most important, this is what regular expressions look like. They are horrible. I know some people like them. If you are one of those people, then I apologise. I wish you all the best. I'm glad to live in a world where some people like this. I am not one of those people. It is quite a complex kind of language. I particularly love these memes which sum up my thoughts on regular expression quite well. That to me, I know a lot of you are new to coding. If I'd presented you with that a couple of weeks in, I doubt there'd be anybody left on the program. That's, I think, pretty nasty. So regular expressions aren't very friendly, I think it would be fair to say. Reason 2, even if you love and are good at regular expressions, well, actually, it's not a great approach. There are numerous issues, because there are huge numbers of potential combinations of POS tags that can form definite noun phrases. So we just looked at a couple of examples there. there are huge numbers, and you'll find that some of the rules that you write will also pick things up. They will pick up the definite noun phrase, but they'll also pick up things that aren't definite noun phrases too. And so you've got a whole sensitivity versus specificity issue going on. Indeed, many years ago, I played around with a little tool that allowed you to try and write various regular expressions to try and pick up noun phrases, definite noun phrases within a piece of text. And the second you got better at one thing, you got worse at the other. I was there for hours trying to get any sort of kind of decent performance out of it. It is an absolute nightmare. I think it is fair to say. A third problem, which is also quite problematic, particularly I would argue for the kind of text that you're going to likely be looking at. The regular expression approach assumes that the language that we are analysing with our regular expression rules will either be following perfect grammar or at the very least consistent grammar. So there needs to be some level of consistency for this to work because we have to predetermine the rules. Now, if we consider, if we're looking at, for example, some paramedic notes, are we going to see a perfectly formed, grammatically consistent piece of text, or are we going to see some abbreviated notes that the paramedic is getting down in order to convey the important information, but has other priorities that they need to attend to? And so, again, regular expression, that's going to be another problem that you're going to have to deal with. But the fourth reason gives us some hope. The fourth reason we don't use regular expressions so much now is because we have these new transformer-based models, things like Spacey, which, if nothing else, you would take away from today as being magical angels saving us mere mortals from having to deal with regular expressions and the depths and complexities of grammar and definite and indefinite noun phrases and all things like that. So the good news is that these transformer-based models, and the reason they've revolutionised the world of natural language processing, get around these problems. Okay, blimey, I went almost exactly to time. That's a first. Sammy, any questions that have come up so far? With the disclaimer that if you ask me any complicated questions about grammar, I have the right to pretend I didn't hear you.
You may want to use that right here. What part of speech is Mr.? I would have thought Mr. Jones would be a named entity.
So Mr. Oh God, you're going to ask me questions. Does Mr. come under? I don't know. It's not, you're only POS tagging. Please put in the text if you know. You're only POS tagging individual words. Jones would. Sorry, can you repeat the question? Mr. Jones is a named entity. Is that right?
Yeah. What part? The question was, what part of speech is Mr.? I would have thought that Mr. Jones would be a named entity.
Okay, Mr. Jones is a named entity, and you will see things like Mr. Jones being picked up. That is different to the POS tagging of the two words Mr. Jones. The POS tagging of the two words Mr. Jones will give some clues that will help to make a prediction about whether Mr. Jones is a named entity, if that makes sense. So we're not just going on POS tags of individual POS tags. That helps us, gives us clues. We'll come on to a bit of that in a moment. Yeah, Mr. Jones is a named entity. The POS tags of the words Mr. and Jones, and indeed the POS tags of the words before and after that, will help us to make a prediction about whether Mr. Jones as a thing is a named entity. So a crucial thing, probably this is a good point actually, I didn't mention. POS tags are done on individual words, including individual names within a name. A named entity can be, and often is, multiple words. Okay, so POS tags are word-based. Named entities can be one to many words. Hopefully that slightly answers it without me having to get too deep into grammar.
I think that does. And the only other one I've spotted is there was a question about whether what happens with parts of speech which are present in other languages but not in English. Am I right in saying there's different kind of flavors of Spacey for different languages?
Yeah, so we'll come on to that when we talk about Spacey. So obviously we're just looking at the English applications here, but there are when we come to Spacey, you'll see that there are various Spacey models. We use these pre-trained models, and we're using today an English pre-trained model, a model that's been pre-trained on English text. But there are loads of models, including stock Spacey models, that are trained on other languages. So yeah, absolutely, you can do this with other languages too. We'll just be using the English model, but the same process, exactly the same process, will apply for any language, as long as there's a model for it.
I think that is everything.
Awesome. Okay, then we're bang on time. Fantastic. Okay, so there's more to talk about, but let's just take a little bit of a break initially now. So what I want you to do, because we're about to get into talking about transformers, I'm going to put you into your groups for about 15 minutes, and then you'll have a 10-minute break. So we'll resume just after 10:30. And I want you to basically just have a chat in your groups about some potential ideas for named entity recognition that you might be able to think of from your own organisations. When you come back into the main room just after 10:30, I'll ask you just to pop those in the chat so others can see what you've talked about. Okay, I'll open up the breakout rooms, go and have a chat for 15 minutes, and then take a break, and we'll be back just after 10:30. Hi everyone, welcome back. Okay, so I quickly popped into a few rooms there before the break, and some really interesting discussions going on. So please keep sharing those in the chat. Some really good, interesting stuff coming out of that. So we've talked a bit so far about what named entity recognition is, and also about the way we are not going to do it. But a little bit about how we would find them in using sort of more traditional methods. But we touched on just before the we sort of went to the exercise. We talked about Spacey and about how this was a transformer based model, and how these are essentially going to help us enormously for tasks such as this. So let's talk a bit about transformers now. So transformers basically have, pun completely intended, transformed the world of natural language processing. Largely due to a model that was developed by Google some years back now, called BERT, which stands for Bidirectional Encoder Representations from Transformers, which was absolutely revolutionary. And we'll talk a little bit about some of BERT's intricacies and in terms of how it learns a little bit later. But it's a little bit different to how Spacey works, but the principles underpinning it are the same. So we're going to talk generally about transformers and use a bit of an example of how BERT does it. And as well as that, there was a previous model that I think from the previous year also developed called Elmo. And yes, BERT Elmo. If you're wondering why there's a Sesame Street theme to this session, that's why there's a whole Sesame Street theme running through natural language processing for some reason. We're not quite sure why, but there's this thing that a lot of things seem to be named after Sesame Street characters. So Spacey, which is the package that we're going to be using, link to it there, is free and open source. Of course it is, that's why it's on this course, but is probably one of the most widely used natural language processing packages in the world now. I remember some years back Mike went to a conference in Texas, Python conference, and went to the natural language processing stream and said that basically everyone just uses Spacey now, which is really interesting in itself. One of the things that Spacey can do is named entity recognition, but it can also do other things. Now we're going to be focusing primarily on the named entity recognition bit of Spacey, but just be aware there are other things, lots of other things that it can do too. So previously, before I think it was a few years ago now, Spacey version 2 and the former Spacey didn't use transformers, the older versions. They used something known as a convolutional neural network, or CNN. So a convolutional neural network, obviously you know about neural networks now. A convolutional neural network is a type of neural network. And it's very commonly used for image processing and historically for natural language processing too, and still is used a little bit. Basically, a convolutional neural network, the best way to think about it is it's kind of just looking at a bit of the data at a time. So imagine like a window that you're gradually sliding across your data. So it's looking at this bit of the data, now slide it across, now it's looking at this bit of the data, now slide it across, etc. That's what a convolutional neural network does. So for image recognition, that basically means you're looking at a little bit of the image at a time, and the feature data that's being fed through is the color data, the brightness data of various pixels that are in that window, and that's providing information to try to identify various objects. In a natural language processing context, you're essentially sliding your window over your text. So you're looking at a subset of your text, a subset of your words at any one time. And so essentially what you're trying to do if you're using a convolutional neural network approach for natural language processing and for named entity recognition is you are trying to identify, looking at this group of words in my sliding window, looking at the words before and after something, do I predict whether this thing is a named entity, this word or group of words is a named entity? And I'm also looking at the POS tags of the words before and after. I'm looking for the distance of the words before and after from the thing I'm trying to predict, etc., etc. Which is how it used to be done. But there is a significant limitation to this approach, and this is the reason why Spacey and other approaches don't use this now. My Spacey uses this thing called transformers. So let's study this following paragraph. My cat is called Prince and he's very demanding. Every day he asks for treats at 11 o'clock. His 11s, I've actually just given them to him on the break, so hopefully that'll satiate him. You could set your watch by him, so accurate is he in asking for them on time. Sometimes when I'm teaching, he has to wait for them, and he gives me a look that he's clearly not happy about this. Now, if we were to read that paragraph as a human being, there are things that we are doing without even thinking about them. We're not even aware that we are doing them, that we are relating things that we read in the text back to stuff that we read earlier. And just to flag that up, let's think about this. So here we said, my cat is called Prince, and he's very demanding. So here, the he clearly refers to my cat, who's called Prince. But even further down in the text, down here, you could set your watch by him. We know still that we are referring to my cat Prince. Even down here, he gives me a look, he's clearly not happy about it. That's, again, referring, the he here is referring to Prince. We are doing that automatically. We are referring linking back to prior information that we've read, that we've consumed, that allows us to identify in this case, what the pronoun relates to. The same here with every day he asks for his treats at 11 o'clock, brackets his 11s. We know that the 11s relates to the treats. And when we talk about them down here, we are aware that we are talking about the treats. That he has to wait for them, and he gives me a look, he's clearly not happy about this. The this here is referring to the wait. We do this so naturally as human beings that it's difficult for us to kind of think about the fact that we are doing that, but that's exactly what we are doing. The problem is that the convolutional neural network approach to natural language processing, where we're sliding a window gradually across our text data, doesn't allow us to do this, because it is only looking at a bit of the text at a time. So unless the information is still within the bounds of that window, that information is lost. And so what happens is the closeness of words, their proximity to the thing that we are trying to predict, becomes important. In fact, it becomes too important, and it becomes very poor at predicting these what we call long-range dependencies. These are words that relate back to things that are much earlier in the text. So, an example here, down here, this is almost a long-range dependency here. But you can have them sort of much further as well. I particularly love this joke here, and I hopefully you will now find this hilarious. Human, what do we want? Computer says natural language processing. The human says, when do we want it? And the computer says, when do we want what? And that's basically a summation of the convolutional neural network approach to natural language processing that basically was the traditional way of doing things. But there is a better way now. And the alternative to this problem is to use something known as the concept of attention. So what do we mean by attention? Well, basically attention is where we put portions of text data up against each other in a matrix, and we basically represent the relationships of each word in on one axis with the relationships of each word on the other axis. Now that turns out to be really useful for things like translation. So we could put the English language version of the text here. Here we've got the French version of the text down here, and we can use an attention matrix in order to try and translate this text by identifying the way in which the English words relate to the French words and vice versa. But here's the clever little trick. You can also, with this concept of attention, put exactly the same text on each axis, and therefore represent the relationship of words within the same text to each other. Okay, and this is known as self-attention. It is so commonly used now when we talk about attention that people just tend to refer to it as attention, but technically it's slightly different. Technically it is self-attention that we're talking about, but very often when we talk about attention in natural language processing, we actually mean self-attention, where you're putting the same text on both axes and essentially relating, looking at the relationships of words within the same text to other words in the same text. And basically what that is doing is emulating exactly what we are doing as human beings when we read the text, exactly what we just did when we read that paragraph about prints in the streets. So let's consider the following sentence that we looked at earlier. Dan asked Sammy if he could borrow her pen. Now, as human beings, if we read that, it's likely that we're going to assume that the thing I want to borrow from Sammy is a pen that I can write with, a writing instrument, rather than a female swan or an animal enclosure. But syntactically, there is nothing to say that I could be asking to borrow her female swan or Sammy's animal enclosure. But we as human beings are making that judgment call that we are assuming that I am asking to borrow her writing instrument, even though that exact same word, pen, would be used in all those cases, and indeed would be POS tagged in the same way. It would be a noun in all three cases. Sometimes additional text can help us to understand the context. So if the rest of the text says something like, "This is because Dan was busy writing his memoirs," then that helps us to identify, well, it's probably a writing instrument he's after, because that's probably more useful for writing my memoirs than a female swan. And the key thing to take away from this is that in natural language, the same word can be used in different places in the same text to mean very different things. And this is known as polysemy. And it's the thing that helps us to try and understand what we mean by a particular usage of a word is the context of that word within the sentence or even within the wider text data. And the clues that are within the text and sometimes external to it, so common phrases, etc., can help us to try and understand the context in which a word is being used, and therefore the context in which that word and that piece of text should be interpreted. So why am I telling you all this? Well, transformers use attention as one of their central concepts. Okay, and this is why they've become so powerful. They use this concept of attention, or more specifically self-attention, to try to understand the context of a word, and then they encode that information about context alongside the word itself. So unlike the traditional approach where you're using a convolutional neural network, you've got this sliding window where you're just looking at a piece of the text data at any time and looking at the words that surround it, and the closeness of those words is kind of influencing the predictions that you're making. A transformer can pull information from anywhere within the text in order to understand and try and understand the context of a word or a series of words, and that's what makes them so powerful for natural language processing, but also for deep learning more generally. And in fact, there's a whole field looking at the use of transformers beyond natural language processing, because they are such powerful mechanisms. So we know that transformers now use this concept of attention or self-attention to link things up within text to understand the context of words that are being used. But at the same time, we don't want to link up everything, because if you've got a big piece of text, the majority of that text does not relate to each other. Okay, a lot of it's not going to matter. So instead, they use this concept of using weights, exactly as you've seen in machine learning approaches, to try and indicate which aspects, which linkages are more important. And when we talk about these aspects in natural language processing, we're talking about the individual words within our text. So, and the way it does this is by using something known as an encoder. Now, I'm going to give you a very high-level explanation of how this works, but there is a really nice explanation here at this link if you want to find out a little bit more about encoders and decoders. It's quite a nice, easy read. So, an encoder in a transformer will basically take some raw text input. I say raw text input, it needs to have been converted into numbers first, and put into a form that the encoder can read. So, as we talked about vectorization last week, and we'll look at that again more today, this concept, we can't just give raw text to an algorithm, to a model. We need to convert it numerically initially, because effectively mathematical operations will be performed on it. But we're going to put in that encoder will take that raw text that's been converted into numbers, and it will extract various features from that input text. And in a lot of transformer models, BERT included, the encoder is not a single encoder, but actually a number of layers that represent one big encoder, each of those layers being an encoder themselves, and then the final layer kind of represents the features that are extracted out. So, as an example, the features that are extracted by BERT include that self-attention structure that we talked about before, which allows it to determine the kind of those weights for that linkages between words within the same text, which allows it to understand what's most important for determining the context of any word or series of words. So this is kind of what an encoder looks like. It will take inputs. This is your raw text turned into numbers, and it'll go through a series of encoder layers, and it'll spit out the other side this feature information that is going to be so useful for trying to understand context. Now, just as we have encoders, we also have decoders. And a decoder in a transformer basically takes the outputs from the encoder Remember, the outputs from the encoder are the feature data that's been extracted from the raw text that's been fed in, and the decoder then uses that to generate some kind of text output. So, as an example, you can use an encoder-decoder set up in a transformer to undertake translation. You would feed in some text in language A. So, let's say the text is "Dan is amazing." You'd feed that into the encoder. That would extract the features that would then in turn be fed into the decoder, which would then spit out the other side the text in language B, and therefore translate this original text into this. And this bit here, these features, that includes that self-retention, context, weighting information. Now, it's also important to say that not all transformer models use a decoder. Some of them just use an encoder, and in fact BERT, which is the big one that was used for so long, does not use a decoder. It just has an encoder. It's basically a pre-trained model that doesn't generate language out of the box. If you take the BERT model, it won't automatically then you can't just use BERT and expect it to work like ChatGPT, for example. Okay, it won't do that out of the box. You can create that, but it won't do that out of the box. Instead, what you do with a model like BERT that's just got an encoder is you apply something known as fine-tuning, which is where we add to that initial pre-trained model so that it then becomes fine-tuned for your particular problem and can then do the thing you need it to do. So just worth flagging up that just because we're talking about this encoder-decoder structure doesn't mean that all transformer-based models have an encoder-decoder structure. They'll all have an encoder, but they don't all have this decoder. If you've got an encoder-decoder thing, you've got a kind of complete model where you can feed something in and something then comes out the other side. So we've talked a lot about things like BERT, GPT. You are all, I'm sure, very familiar with GPT being the transformer model that sits underneath ChatGPT. ChatGPT is just the interface that we use to interact with the GPT model. And indeed, Spacey's own pre-trained models. These are all examples of what are known as LLMs, or large language models. And these are models that have been trained on huge amounts of data, extremely large corpuses of text data, that can then generate and understand natural language really, really well because of this transformer-based architecture and this concept of attention that they use. By the way, when I say extremely large corpuses of text data, I really do mean it. So just to give you an example, the original BERT model back in 2018 was trained on 3.3 billion words from Wikipedia and Google's book corpus. These are huge, huge models. You can't, even my really nice PC down here would struggle to train from scratch a BERT model, okay? And that's why you don't tend to do that. And that's why you tend to take a model off the shelf and then fine-tune it. So one way in which models like BERT learn is by using something known as MLM, or masked language modeling. So you're probably thinking, well, how do you're feeding in all these 3.3 billion words? How's it learning this kind of thing? And there's different approaches to the way in which it tries to learn the context information within our text. So to understand, try and understand how masked language modeling works, let's play a quick game of nothing. Why is that not a bit? Oh, there we go.
And appearing tonight on John Jones, Beryl Reid, Arthur English, Gillis Watley, Spike Milligan, Sandra Dickinson, and here's your host on Terry Wogan.
Okay, so yes, I am going to teach you the complexities of training. Oh God, no, let's not play that again. I am going to teach you the complexities of transformer-based architecture training using the game show Blankety Blank. I'm sure many of you are familiar with the game show Blankety Blank, but for those of you who aren't, it's incredibly simple. I'm going to give you a piece of text, but one of the words is going to be missing and is going to be replaced by a blank, and you are going to have to decide what you think the missing word is, and I want you to post in the Zoom chat what you think the missing word is, the word that's been blanked out, okay? And then I will tell you what I believe, what my answer was for the missing word, and let's see if we agree. So let's have a look at our first sentence. Dan got in his time machine to get some more references for HSMA. He put on his aviators and dialed in the blank as his destination. Off you go, put in the chat, what's the blank?
Blankety blank, 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 blankety blank.
Okay, so hopefully we've got some answers. Before I give my answer, I'm going to just ask Sammy what's come up in the chat. What are people saying is the blank?
We have a range of answers, including the year, the date, nearest blockbuster, the route, the coordinates, the overwhelming, you may not be surprised to hear, is the 80s.
Indeed, and my answer was indeed the 80s. So bing, bing, bing. Well done to those who said the 80s. We've got a match there. Fantastic. Okay, so let's move on to the next one. It was a rainy day and Sammy couldn't decide what to do. Suddenly she remembered her large collection of blank and thought that should keep her entertained, though perhaps not the neighbours. What's the...
Blankety blank, 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 blankety blank.
Okay, Sammy, what's come up in the chat?
I'm appreciating all of your thoughts on my collections. I'm glad to say that, that some of the suggestions include female swans, musical theatre CDs, indeed correct. We have drum and bass records. We have, what else do we have? Guitars, drum kits, pneumatic drills, tap dance routines, video games, PC mods, venomous snakes, Jupyter notebooks, very good question, very good guess, and also very popular answer, instruments.
Indeed, and Sammy, can I ask what your answer would have been to that blankety blank?
It would have indeed been instruments.
Indeed, that's exactly what I had as well. So fantastic! Well done to everybody that said instruments. You've remembered the introduction session to this program well. So why have we just played blankety blank? Or why not? I would say first of all, but this is basically what masked language modelling is. Okay, it's blankety blank. It's one. A masked language model is one in which it is trained to predict a masked or hidden word in a sentence given the context of the words that surround it. And it does that by looking in both directions. So it looks both before the missing word and after the missing word. And by the way, that's where in the BERT model, which is an example of a masked language model, the B, which is sort of for bidirectional, that's why it's called a bidirectional model. It's because it looks in both directions, trying to make its masked language predictions. Now, the words that are selected to be masked are typically random, and they will be a certain percentage of the words. So to give you an example, in the case of BERT, it's a random 15% of the words are blanked out, and it has to then try and predict what those words are, and that's how it part of the way in which it trains. It also uses something called next sentence prediction, by the way, which is quite an interesting thing in itself, where it gets given two pairs of sentences and it has to decide whether it thinks those sentences are related to each other or not. So that's quite an interesting thing as well. But this master language modelling, this is basically exactly what you just did when we played blankety blank. In fact, we as humans do this all the time, not just when we are playing blankety blank. We do it in general conversation. If we don't hear something, our brains will try to fill in the blank. If we don't hear quite a lot, if there's too many blanks, which happens more as we get older, then we usually have to ask them to repeat it. But we do this all the time, and we're not even aware we're doing it sometimes. And indeed, when we're reading, for example, we'll often read very quickly, and our brains are kind of doing some work filling in the blanks. We may not have actually looked at a word in many cases. Our brains are kind of filling that information in. But essentially what we are doing, whether we're playing blankety blank or trying to work out what somebody just said, or if we're reading, we are ultimately making predictions just like the model is doing. And just like when you're playing blankety blank or doing any of these things, those models will sometimes be wrong as well. So we need to be aware of that. Now you can actually play around with the masking predictions of the BERT model using this link here, which basically allows you to type in any sentence that you like, and you can mask out a bit of it using this mask token. You just put some square brackets around the word mask in capital letters and click compute, and basically you can then see what BERT will predict to be the missing word. And just to hammer home that this is a prediction, it will then give you the top 5 predictions that it believes, and along with its confidence level for those predictions. So I put in, everyone agreed that Dan was the mask teacher they'd ever encountered. That's my blank. So I played blankety blank with BERT. I was delighted to see that BERT, it was 80% confident that the missing word was best. Slightly less pleased to see that the next top answer was worst, but then relieved to see that it was, if it wasn't worst, that it would probably be either greatest, finest, or strongest. So there we are. So it really indicates the way in which it's trying to essentially make a prediction, because we don't know. It could be any of those things or other things, but it's trying to make a prediction based on the way in which it's been trained and exposed to these 3.3 billion words. So, as I mentioned earlier, that this kind of original training of a transformer model is incredibly computationally resource intensive. This goes beyond just buying a nice Alienware and putting it to work. This is serious stuff to train on 3.3 billion words. Okay, so we don't tend to train these models ourselves from scratch. We tend to use pre-trained models that have already done this for us. So various variants of, you can use the original still now, you can use the original BERT model, but there are various variants of the BERT model that have been trained for different application areas, for example. And the same with spaces. We'll see today, there are various pre-trained spacey models, and you can use different ones for different purposes. And we tend to take those models off the shelf and then apply them for our particular purpose. Sometimes we need to do something known as fine-tuning, which I mentioned earlier, which is still resource intensive, but much, much less complex computationally, but is still only practical if you've got, if you had to do fine-tuning, it's almost essential, I would say, that you have to have a CUDA-enabled GPU or some TPU or access to cloud resources for that. To give you an example, we ran a masterclass on BERT last year, which is where a lot of this content has come from this year. And for that masterclass, we were going to get people to do a little fine-tuning exercise. I got Elliot, who was Sammy's precursor. I got him at the time to test out what it was like, because it was running in reasonable time on my very fast GPU. I got him to test it on what he had, a very, very fast computer, but not using the GPU. It took mine, I think, about 3 minutes, and his estimated time was 2 days. So just to indicate, and that was just for a toy example. So just to indicate, this is all but essential if you were going to do fine tuning. The good news is, in most cases, you can get away without doing that anyway, because there are lots and lots of different pre-trained models that you can just grab off the shelf that will probably be good enough for what you need. But if you did want to fine-tune them to give them a bit of extra training to try and tune them a bit more to your particular application area, just be aware that you can do that, and actually the code to do it usually isn't too complicated, although Spacey's become a bit more complicated for doing that. But you would need some way to access some sort of GPU or TPU resource, because it's just not really practical to do it without that. Okay, so that was a lot of information I appreciate to take in about Transformers, and in the middle we played a game of blankety blank. The point of this is not to get you fully understanding all the intricacies of how a transformer-based model works, but more a sort of broad appreciation and the gist of how these things come to do this stuff, so that when you're using Spacey and other transformer-based models, you kind of get a sense about how these things work. So let's talk about, let's just summarize what we've covered, and then talk about how this all relates to what we're trying to do in terms of named entity recognition using Spacey. So, transformer summary. Transformers are basically large language models that have been pre-trained on huge amounts of text, and they are been trying to understand the context of that text, because that gives us so much more power, and it does that by using this concept of self-attention, where it maps the text to itself to try and understand how words relate to each other. They include encoders, which take in raw pre-processed text as numbers, extract the feature information from that text, things like the weights of that self-attention, and spit them out the other side. And models like BERT, in fact, use a multi-layer encoder, so you have lots of mini encoders that make one big encoder. Many transformer-based models, including BERT, use masked language modeling as a way of extracting information from those text features, getting good at being able to do that as part of their training process. And all masked language modeling is plain blankety blank. So you can now, whenever you see masked language modeling, just think, oh yeah, that's blankety blank. And transformer models take huge amounts of computational resource and time to learn. So normally, if we're using these things, we will take a pre-trained model off the shelf. Sometimes we might fine-tune it with our own data if we need to, but we need access to GPU resource. But typically, we just grab a model off the shelf. So, how does all this relate to Spacey and named entity recognition? Because you're saying, Dan, this is all incredibly fascinating, but surely the name of this session is named entity recognition. I haven't recognized a single named entity yet. Okay, this is all leading up to this, because basically we're going to be using a pre-trained transformer-based Spacey model that is going to predict which word or group of words are named entities in some text based on what it's seen during that training. So hopefully you now have a bit of an appreciation of how these pre-trained models that you're just going to be grabbing off the shelf have got to this point at which you can chuck some text at them and it will just spit out the information you need. And indeed, as you'll see when you come to run Spacey, the single or two lines of code that will do this will run incredibly quickly, because there's no training. These models have already been pre-trained. So we just use that model, Spacey applies that model to our text, and we get out the information. Now, it's also worth flagging, as I mentioned earlier, that Spacey won't just predict named entities. It will do all sorts of things. It'll store all sorts. It does things like predicting our POS tags, for example. Remember those we talked about earlier, about our parts of speech tags. It'll look at dependencies, so we can grab all that information out too. So it does lots of other stuff, but we're going to be primarily looking at the named entity stuff that it grabs out. Okay, any questions about any of that, Sammy?
Yep, so just a couple of small things. I think these have primarily been answered in the chat, but I'll just chuck them to you just for your thoughts as well. Is there any way to add certain words into pre-trained models to potentially improve things like named entity tagging, for example, if you had certain pharmacy medications, so adding them to a list to be recognized specifically?
Yes, there is. So this is one of the disadvantages of Spacey's new way of doing things with transformers. Although the benefits outweigh the cons, I would say. So it used to be quite simple to do that in the old version of Spacey. Well, relatively, it was a bit faffy, but you'd basically open up what's called a training pipeline, and you'd shove your new words in there, and then close it again, and it would learn those words. We even used to teach the code for doing that, which was largely horrible, but you could sort of just copy and paste it and it would work. Because it now uses a transformer-based architecture, unfortunately, that's a bit more complicated, but you can still do it. And we link out to where you can do it. So if you look at the Spacey documentation, it will show you how you can do that. Okay, so yes, you absolutely can. What you probably want to do first, though, because that is an example of fine-tuning, so you will need a significant computational resource, particularly a GPU or TPU resource to be able to do that. So you can do it, but check first whether there are pre-trained models out there that are more skewed to what you need. So to give you an example, just off the top of my head, there is a version of Spacey called Spacey, which is being trained more on scientific things. And we had a project in HSMA 3 that was looking at extracting information from GP patient notes, and it found standard that some of the standard kind of Spacey models were all right, but it didn't pick up on a lot of the sort of individual medications and things like that. Whereas Spacey was performed apparently much better. So they found Spacey was really good. You may even find other models that are specifically been trained on those kinds of things. But I think Spacey from memory has been trained on scientific journals, medical journals, things like that. I think that's why it performs better. But yeah, as an example, you can use, there are models out there for all sorts that you can grab off the shelf. So yeah, but you can, the answer is yes, you can still open up the training, shove in your own examples, but just be aware that is now more complicated because it's a transformer architecture. And I started to look at it and thought that's not coming into the core training. So go and have a look at how you do it. It may be easier than I think.
Fantastic. Yeah, I think I'm also aware of Med Spacey as well, which may be even newer, which is kind of got that specifically clinical slant as well, which is nice. So another question that came through, is fine-tuning in this instance the same as transfer learning? I think my understanding is that they are related but subtly different. But anything to add to that?
Yeah, so I think I mentioned transfer learning late. In fact, I do this afternoon. We'll talk about transfer learning. But so transfer learning is basically where you take a model and rather than try and teach it from scratch, you take something that's already been pre-trained on common stuff, and then you essentially then target your training to your data, so it kind of learns the nuances of your particular data. So rather than trying to train a model, it's like taking a sort of newborn baby and trying to teach it the English language from scratch. Rather than doing that, you take something that's kind of got that's been trained more generally, and then you add to that training via your own examples. I think it would be fair to say that fine-tuning is a specific example of a type of transfer learning, so it would be more a subset of that. But fine-tuning specifically relates to transformer-based models, but yeah, it is a type of transfer learning. But transfer learning is a more general term, basically. You will see an example of transfer learning this afternoon. That by default, the model that you run this afternoon won't train from scratch, but you'll also see that there's a link that you can look at if you want to then turn that one of the layers of your neural network. You can then use a pre-trained layer, and then you're effectively doing transfer learning on that. But we'll come to that later.
Fantastic, thank you. I think there's also, I'll just highlight, there was an interesting conversation going on about whether the tools such as transformers include checking for cases where there could be something like an offensive or incorrect translation based on bias. So there's some nice conversation going on there, but yeah, I think
Yeah,
that's might be.
I mean that's a really important point. Those of you, you cast your mind back to the ethics session, and we touched on some of this stuff a little bit. Um, when we say these large language models have gone out and consumed 3.3 billion words, and more in some of the cases of the newer models like GPT, it's warts and all stuff. So there's some horrible stuff in there. There's some subtle bias in there. So be aware of that. They have consumed all sorts of rubbish in there as well, and that's how these things have learned. So it does have problems. It absolutely does have problems. And in fact, that segues nicely to this little mini exercise I'm going to get you to do now. Just want you to go for the next 10 minutes. We'll come back at 25 past. So take a sort of combined play with this and have a little break. I want you to go to that link, the Hugging Face, where I said you can play around with the masked language modelling and play blankety blank with Bert. Try out some different sentences, mask different words within those sentences, and you might want to go back to some of these issues around bias. And in fact, if you want to explore some of that, try some of these words, these sentences here. Not the thing about cats. I mean, you can try that if you like. Cats are generally. I mean, you should probably just start with that one to see what it says. But try sentences like: the man worked as a mask. The woman worked as a mask. The nurse tended to the patient, and mask spoke to the doctor. See what it comes up with in terms of the predictions, and you will see some of this interesting stuff that we've talked about, bias and consuming all this data in action. Okay, so I'm going to open up the breakout rooms. We'll come back at 25 past. Stop share. Okay, well, camera's gone. Okay, that's better. Yeah, so apologies for that. There was a bit of confusion there. Suddenly panicked thinking it was permanent. I think we may have suddenly just swamped the server. So it went down for some people, but not for others. It did then did come back up. So hopefully you managed to have a play around with that. If you didn't, do have a play around over lunch or something, or after the session, because it's really interesting to look at some of that. So yeah, do have a look. But I'm going to press this on because we're running bang on time, which is a first for HSMA. So let's continue that momentum. And let's actually get on to do some named entity recognition. So let's close this down and let's talk about Spacey. Let's finally get on to the meat of what we're going to be talking about. So let's try and use Spacey. We've got an understanding now, broad understanding of how it works at a fundamental level in terms of what it's doing as a transformer. When we use Spacey, basically this is what it's for named entity recognition. It's basically going to be trying to predict whether a word or a group of words is a named entity based on the pre-training that it's had via all the mechanisms that we talked about. When we use Spacey, there are basically 3 key steps that we're going to take, regardless of how we want to use it and what we want to use it for. So this is the same for regardless if you're doing named entity prediction or if you want to look at POS tags or whatever. So the first step is we load in a pre-trained model. We talked about that we grab a pre-trained model off the shelf. That's the first thing we're going to do. That's sometimes referred to as a language in our terminology. And we can load that into a variable. We can call it whatever we like, but we typically, by convention, call that variable NLP. Okay, it's just a convention that they use. We then apply the pre-trained model, our thing that we've stored into NLP, our language, to some text to generate predictions of all sorts of things. So named entities, POS tags, it'll do all these things, word dependencies. And all of these will be stored in a Spacey structure called a doc object. And we often name that doc object either article or doc. Again, we could call it jam donut if we wanted to. But convention says we tend to use one of these. I tend to use doc, but you may see the word article used instead. But again, you can call it whatever you like, but the convention says you typically use one of those. And then we basically explore the predictions that have been stored in this doc object, and we'll often use Displacy, which is Spacey's fantastic visualization engine to visualize them. And those three steps are all we need to do. So we basically grab our pre-trained model, we store that in Python as a language. We then apply that language to our text, so we give it the text. It'll then do its thing and pull out all these predictions, and then we can then explore those predictions if we want to, using Displacy's visualization. So we're going to be using the supplied environment that came with the repository for this session, which is NLP_NER. That environment we're going to be using, that includes an installation of Spacey. Hopefully you've all seen the note that I forgot to add this bit, this crucial step. Hopefully you all saw that message yesterday. If not, you must do this before you'll, otherwise the thing won't actually work. We have to download a pre-trained model. Okay, so these don't come, although it comes with an installation of Spacey, there is no model downloaded by default, so we have to go and find one. So in the example we're going to use one of the stock Spacey models called NCall Web SM. Okay, and this is basically a model that has been trained on the English language. That's the EN bit, and this is where I was saying there are other language variants as well, and which has been trained on general text from the internet. So that's where the core web bit comes in. So English core web. Now the SM bit indicates the size. Okay, so there are actually three variants of the NCore web model. There's the small version, which is the one we're going to use, SM. There's medium, MD, and large, LG. And basically they vary in terms of the size of the pre-trained model. And specifically what I mean by that is the number of word vectors that are included, ranging from none, which is the one we're going to be using in the small, to over 500,000 for the large one. Obviously the larger models are much larger to download, and the smaller models tend to have lower accuracy than the larger models, but they are more lightweight, and may well be good enough. So as ever with modeling, always start with a simpler model and see if that's good enough for what you need. So it's a good starting point. So just be aware, so for simplicity for this training, we're going to be using the small version, but be aware there are, even on this standard stock model, there's a medium and a large version that you can use as well that might give you better performance. So to download the model, and indeed to download any Spacey's models, we have to perform a command prompt. If you've already done this as per the instructions I posted yesterday, you don't need to do it again. You only have to do it once per model. We go into a command prompt. I can't remember if you have to go into, I don't think you do. But just to be on the safe side, you might want to switch into the NLP environment first. I don't think you have to do that, but conda activate NLP NER just to be on the safe side. And then basically you type into either a command prompt or your terminal or the Anaconda prompt, or whatever you want to do it. You type this Python space -m space Spacey space download space, and then the name of the model that you want to download. In this case, that's NCore Web SM, and that will then download the model to your computer. I saw a bit of conversation about where it puts it. I don't know offhand. You won't see it. It's slightly hidden away, but it is there. Okay, so it will download that, and Spacey downloads that into its repository, so you know you then have that model to hand. So. Assuming we've done that, we are going to have a look at the code example, the NER example.py. This piece of code is going to try and predict the named entities in a news story about Alan Titchmarsh's trousers. Okay, this is what our task is this morning. So let's have a look at the NER example.py. So I'm going to switch over to, let me get rid of this. I'm going to switch over to VS Code. I will just make that a little bit larger so you can see it a bit better. Okay, now you'll see there isn't much code here. In fact, half of this code is just to do some print messages so you can see what it's done. And a lot of it is also comments. So this is actually really straightforward to do. First things we're going to do here are to import the things we need. As always, we're going to import Spacey, and we're also going to import NCore WebSM. That's the name of the model, the pre-trained model that we've downloaded. Okay. If you haven't done that download thing, this is where it's going to fall over, and it tends to come up that it can't find a module named Spacey. But what that means, as long as you're in the right environment, you haven't done the bit of installing the model. So once we've imported, we're going to then load in the pre-trained model. This is step one. We're going to load that pre-trained model into our language, and we're going to call that language NLP. So we just call the .load method of the pre-trained model, and that loads in that Spacey model into NLP. So now we can just refer to NLP, and that is the loaded pre-trained model NCore WebSM. Okay. Then we're going to read in the document for which we want to extract the named entities. In this case, this is titchmarsh.txt. Let me just bring up titchmarsh.txt so we can see what it is. This is the news story about Alan Titchmarsh and his trousers. This is the text that we are going to try and extract, from which we're going to try and extract our named entities. So all we're going to do here is, this is fairly standard. We're going to open the file with a with statement. We specify the encoding here as UTF-8, which is normally what you would have for these text files. And we're just going to simply call the .read method on the file, which will basically just read everything in as one string, just as you saw last week. The only extra thing we're going to add is a .strip. This basically does exactly the same thing, but it then also strips out any white space at the start and the end of the file, if there is any. So it can be quite handy to do that for these kinds of text files. So that will read in the entire text into one string, which will now be, I've called raw read. Then we're going to apply the pre-trained model, our NCore WebSM model, to this raw text to extract named entities and all sorts of other things as well. But it's part of that is going to extract our named entities. And all of the Spacey's prediction, including the named entity predictions, are going to be stored as a doc object. I've called my doc object doc, but again, you might also see it named as article as well. But as I say, you can call it whatever you like, but the convention is to call it either doc or article. I prefer doc myself because it's a doc object. And the way we do that is we just give the name of the model, which remember is NLP now. We say take that loaded in model, and into that model, I'm going to pass in the text I want you to do stuff on, which I've read in here as raw read. Okay, so it's literally pass the text to the model. That line of code does everything. That's how Spacey does its thing. Because remember, it's pre-trained. We haven't had to train it. This is already trained. So this will now go and grab all of the information that we want. And then once that's happened, then we can do what we like. So here I'm just going to basically store the various named entity categories. Remember, that's things like person, org, norp, all those things we went through at the start. They are actually stored for each entity in Spacey. They are stored in an attribute called label underscore. That will store the category for a predicted named entity. So you have a named entity, and then you can, if you want to grab the category of that named entity, whether it's a person, a place, or whatever, this will, if you access the .label underscore attribute of that entity, that will grab out what the predicted category. Remember, it's just making predictions, so what it thinks the predicted category is. And the named entities themselves are stored as in doc.ents, or if we called it article, it would be article.ents. It's the .ents bit of our doc object, basically. So this, I've just used a simple list comprehension here to say, give me a list of all the labels, which, remember, we start reading them from the middle. So we say for each X in docents. So in other words, for each predicted named entity in this text, give me its predicted classification, the label. And then I'm just going to print them out, basically print out the label, print out the entity against the label. So let me just run that. So again, this is just an added bit that I've done just so that we can see how it's worked. The actual core of the code is this. And in fact, the bit where the magic's happening is here. So let me run this in an interactive window so we can see what happens. And I'm in the wrong environment, so I close that and then I go into the correct environment. Definitely did that on purpose. And I run it again. And let's see what happens now. It should take a second. There we go. So we can see from this, it's done it very quickly. Spacey has generated predictions of what it believes are the named entities within that news story about Alan Titchmarsh's trousers, alongside it's given both the named entity and what it believes is the predicted category for that named entity. So it's picked up Alan Titchmarsh and it believes that's a person. Seems to have got that spot on. North Korea, a geopolitical entity. Seems to have got that spot on. 2022 as a date. Britain, geopolitical entity. BBC, it's picked up as an organisation, etc., etc. Picked up some. It's not got everything right. We can see if we scroll through. It thinks Titchmarsh is an organisation. It thinks Garden Secrets is a person. Now you will also see things repeated. So you can see Titchmarsh appears twice here. In fact, maybe even 3 times, 4 times. Every time a word or group of words appears, it is predicted to be or not a named entity. So you can end up, and it can sometimes the same words might be predicted to either not be a named entity in one place and a named entity over here, or even a named entity of different types, because that could happen in real text. So you will kind of see that. But if you scroll down here, it hasn't done a bad job. It seems to have done all right. It's picked up some sort of key bits. Remember, this is just on the using the standard stock model that's trained on general web stuff in English, but using just the small, lightweight version of that model. My favourite one, though, is where it thinks the Dulcet Yorkshire is a person, which is a great name for a person. I'd love to meet a person called Dulcet Yorkshire. Okay, so that's it. That's done it. We've grabbed out our named entities. We've done some named entity recognition, and it's actually really simple using a Spacey pre-trained model. Now, I mentioned that Spacey also comes with this fantastic visualization engine called Displacey, and we can use Displacey to easily visualize Spacey's predictions about various different things, one of which is named entities, which is what we are looking at here. And it's actually really easy to do that. If we want to use Displacey, we simply import Displacey, and then we just add this line of code anywhere after the pre-trained language models have been applied to the doc object. So that line of code here, where all the magic happens, anywhere after that, we can then run this line of code where we say spacey.displacey.render, and then you tell it the thing you want to render, which is our doc object, and then style here basically says what you want to visualize. So here ent means the predicted named entities. Okay. Now just to flag up, so we'll have a look at this working. This command will work as long as you are in a Jupyter style environment. So if you're in Colab, it'll work fine. If you're in a Jupyter notebook, it'll work fine. If you're in VS Code with the Pi files we are, and you're running it in an interactive window, that puts you in a Jupyter environment, you're fine. Just be aware, if you're running it in a non-Jupyter style environment, you can still do it, but you have to use .serve instead of .render. What that will do is it will fire up a server instance instead. Now, if you do that, you will likely find your firewall blocks it because it has to spin up a server. Effectively, the same thing is happening here with the .render, but there's already a server spun up. It's using the Jupyter server, which you should all be able to use fine because that's all installed and you're using Jupyter all okay. So it just uses the Jupyter server to do it. But if you're not using Jupyter, in other words, you're not using VS Code in interactive mode, or you're not using a Jupyter notebook, or you're not using Colab, then and you try to do it any other way, then you will need to use .render and it will spin up its own environment. So just flagging that up. But you should all be fine if you're using any one of those. So let's go to the Displacey example. You can see I've just added in import spacey.displacey and then just added this line of code down here. So rather than all those print statements now, I've just got this single line of code. Let's see what happens when we run this in interactive mode. Bring that across, and there we go. We've got this is our text review, and you can see what Displacy has done is it's automatically, let me just move this, it's automatically flagged up what the predicted named entities are, where they are, along with the predicted category for that named entity. So it's picked up Alan Titchmarsh here being a person, etc. And it colour codes them for the different types. So organisations, it's obsessed with thinking Titchmarsh is an organisation, but it colour codes those all sort of kind of light blue, etc. Really is that easy. And that's a really nice, easy way to very quickly grab out some named entities and see where they are in a piece of text. But of course, as I mentioned, Spacey's not just looking at named entities, it's also grabbed out lots of other information as well. And in fact, we can visualize that, so we can see that it's not just named entities that it's pulled out. So one of the other things that it's done is to look at sentence dependencies, syntactic dependencies within our text that it has parsed. So if we want to look at that, we can just change the style in our render statement for Displacy to dep, and that will then show the dependencies, syntactic dependencies. Just a tip: if you're going to do this, it's usually best to then break down your text into individual sentences if you've just read it in as one single string of text, which we have here. And you can do that easily using this code here. That will break it down into some sentences and then render on the sentences rather than the doc object. And that will basically, it gives you a list of doc objects, but they are split down into sentences, and it will do that for you. So let's have a look at that code. What's this thing go away? This one here, which is exactly the same as say, but I've just split it into sentences, and we're going to display the dependencies this time rather than the named entity. So if I run that, and by the way, on the Spacey documentation, you can see lots of different visualizations that you can do and tweaks that you can make to it, and it explains how to do all of those things. And you can see here, it's come up with the sentence dependencies, so you can see how North and Korea are linked to each other, and all of these weird acronyms that you see across here, some of which you might be able to work out what they are, and then others you're looking at a little bit confusedly, particularly if grammar is not your forte. So a little tip, you can actually, if there are abbreviations that you're looking at and think, I don't know what that abbreviation means, you can actually use spacey.explain to give you a short description of what that abbreviation means. I should emphasize the word short. It will literally just unfurl the abbreviation. And if you're anything like me, with most of them, you'll then look at that and think, I still don't know what that is. But you will then have the actual name of it that you can then Google and find out what this thing is. So some of them are fairly straightforward. So, I mean, you probably guess prop n is a proper noun. But if you call spacey.explain, in fact, let me show you. If I go into the console, you can just do it live from here. Spacey.explain, if I see something up here, I can see n subj there. So I'll put that in as a string, n subj, run that, and that has not worked. Why has that not worked? Oh, it's because I've typed it wrong. I've missed the S. There we go. There we go. Ah, right, good. Now I know n subj is a nominal subject. Good. Good. The next step is I go to Google and Google what on earth is a nominal subject. So this doesn't teach you grammar, but it will unfurl the abbreviations to give you the thing that you can Google. Yeah, nice little shortcut there if you want to get into looking at sentence dependencies. And as I say, there's lots more that you can learn about Spacey visualizations in the Spacey documentation. This link here takes you straight to the visualization bit. Shows you how you can use different colors, and you can also do things like embedding in web apps, including Streamlit apps, which Sammy's going to go into in Module 7, teaching you how to build your own Streamlit apps. Spacey's got his own ways in which you can integrate really easily into nice little web apps like this. So you can create a nice little named entity recognition model with a little web app that will automatically, so a user can upload their own text data, and it'll spit back the predicted named entities. So that's quite a cool little feature. Okay, any questions, Sammy, about any of that?
So only thing that's come up is a few people are having issues with the install process. People getting saying no module namespacey, for example. Does seem like people are finding that being within Anaconda prompt, activating the environment does seem to be helping for some people before running that install process. I have just posted some collab instructions as well for anyone who is not able to get it working. It will work through collab, but do shout if you have any issues with the instructions I've posted around collab. I'm happy to have a look and see what I can do there.
Brilliant, thank you. Yeah. So if it comes up, there's no module named space. It usually means the model hasn't downloaded correctly, or something's gone wrong there, or you haven't done it. It might also be. I don't know if it will make a difference. Sometimes you may need to restart VS Code to kick it back into gear to get it to pick up the model. So that might be worth a try as well. But it should be, assuming you've got your environment, you've switched to that environment, and you have then installed the Python, the Spacey model using the Python command. It should then work. So yeah, there shouldn't be any other steps. Okay, great. In which case, we can't believe how much we're on time. This is all going to go wrong this afternoon. This afternoon is the hopefully one of the most fun sessions we've ever done, but also one of the most convoluted in terms of stuff that we're going to do. But hopefully it'll be fun. But we are nonetheless running bang on time now. So what I want you to do for the remaining 40 minutes before lunch is you're going to work in your groups. You're going to have a look at the instructions in the exercise 3 instructions PDF that I've supplied to you. You're going to basically try to write some code that undertakes some named entity recognitions on a public dataset of 1 million news headlines from the Australian Broadcasting Corporation, ABC. So this is a dataset I grabbed off Kaggle. Don't forget to use the NLP NER environment, and don't forget you will need a Spacey model to do this. You might want to try different Spacey models, of course, as well, but start with a small model. And also be aware, if you haven't downloaded the large models, this is going to depend on your internet speed. You are also connected to Zoom, so that might cause problems if your internet speed isn't great. One thing to flag up is that the dataset you've been given has been stripped of capital letters. Now, that isn't ideal for named entity recognition, because often you want to keep capital letters for named entity recognition, because they themselves can help to identify what might be a named entity, because that can be a clue. It can be misleading, but it can help. But I want you to see how well Spacey performs or doesn't on this data that has all the capital letters stripped out. So basically, you're going to be trying to extract named entities from a series of news headlines. Okay, right. I will put you into your groups as they follow the instructions in the PDF. Have somebody sharing their screen and work through this as a group. Read through the instructions carefully and gradually work your way through it. You may not get through all of it before lunch. You might, but just try to get through as much as you can. I have lost my bar. Oh God, how do I get it back? Oh, that's not working. How do I stop? I am sharing, aren't I?
You are, yeah.
Yeah, I can't. The shortcut to get my bar back is not working. It is. Oh, hang on. It's because error between chair and keyboard there. I was pushing the wrong key combination. There we go. Right, that's better. It would help if I actually push the right keys. Right, stop talking, Dan. Open up the breakout room.